So thank you very much for inviting me to this workshop. So my talk is about sequential analyses on open datasets. So thank you very much for the introduction, but I also thought very quickly to just say something about me for those who may never have heard of me before. So like you said, I work with temporal network theory and neuroimaging. I'm also, and this may be quite important for this talk, is that I'm also what is known as a research parasite, which is somebody who uses data and collects very little data themselves. And also, as you said, have an increasing interest in meta-science. And actually my original background was in philosophy, so I'm quite interested in the philosophy of science as well. So the topics for today, the plan is to talk about statistical inferences on open data, and if there's any problems regarding this and what we can do about it. It also kind of naturally leads into this distinction between confirmatory and exploratory analyses. And these two may not seem to be linked straight away, but there is a link between them, and we'll get to that as I progress. What I'm basing a lot of this work on is a publication that came out about 2 months ago now in eLife called Dataset Decay and the Problem of Sequential Analysis on Open Datasets. So if you want to read more technical details that I may not go into, you can look up this paper. Okay, so first off, I want to state something very basic, which is that open data is very good, and it's very good for science. And I maybe see the reason why I'm saying that is because we maybe seem to be critical to open data here, but that's not our intention at all. So firstly, it's great for reproducibility. If I publish some analysis and you want to get the exact same results as me, open data is great, or is necessary if we want to have reproducibility. It also allows us to reuse data and get diverse opinions, and the rise of these research parasites that I'm one of that use data to ask new questions. These are all good things, and it's something that we want and we want to encourage. And all the co-authors of the paper that we wrote all believe in open data. So this is not a talk saying that we should not have open data. But why could you interpret this talk as being critical to open data? And the way I would answer this is because some people, for example, they see open data as something extremely good. We don't have enough open data, so the main goal should just be to acquire as much open data as possible. That should be our goal. We can be critical later. Whereas I'm kind of a slightly different, and I fully understand if you have that perspective and get a bit angry at me for being critical. However, my way of thinking is that since open data is good for science, and what I care about more is not open data as some intrinsic property, but I care more about open data because it's good for science. That's why we want it. So we want to also make sure that the practices we use with open data are also good, because we want science to be good. That's my thinking here, at least. So when we started out with this project, we decided about 3 reasonable desiderata about open data. And we think these are kind of like 3 different kind of like assumptions which most people would accept. Not everyone accepts them, but most people accept them about open data. Sharing incentive. So firstly, we don't want the data producers. So if you make some data, we don't want the initial analysis that you intend to do to be negatively impacted just because you share your data. This seems quite reasonable, because if we don't have this, then people won't share their data. They would rather be egoistic and just keep the data for themselves, because if they share it, then they're negatively impacting themselves somehow. We also want open access. We want, I mean, this is almost tautological. We want minimal or no restrictions to be placed on the data, because if we have restrictions, then the data are no longer open. So open access is really important. And thirdly, we would also like to have quite a stable false positive rate. We don't want the false positives to increase just because we're reusing open data. And this is kind of like a joking summary. I've given this talk about quite a few times now, and nobody seems to recognize this kind of joke internet phenomena from a couple of years ago, where you have a triangle and you have to choose two of the three options. And kind of the summary or the conclusion of the article of this article or this argument is that we only can seem to have two of these very reasonable desiderata that I said a second ago. So the argument, what is the art that I'm going to put forward for today? It consists of several different components where together all build up to kind of show this possible problem of sequential analyses on open data. So firstly, I need to do the distinction between sequential and simultaneous analyses. Then I'm going to spend a lot of time talking about statistical testing and sequential correction procedures and the different consequences of this. Then I'm going to show some kind of an empirical example of combining the two. So if we don't take sequential comparisons seriously, what does that lead to? And then finally, I'll talk about some possible solutions that we can consider about how to maybe mitigate the problems that this could create. So let's start off very simply with this iconic picture of showing a empirical analysis, and this symbol here is supposed to represent data. So we get some data, we collect some data, we then analyze this data in some way, and then we publish or we disseminate this knowledge to the scientific community, often with a scientific article. And then an ideal scientific enterprise would have first experiment, we collect data, we then analyze the data, and we then publish the results. And the second one, we get some new data, we analyze the data, and then we publish it again. But in practice, what we often do is collect a data set where we do multiple comparisons, multiple statistical tests per data set, and we then publish these results together. And sometimes we will correct for the number of statistical comparisons we do, and sometimes we won't. It depends a bit, and I'll get into that in the second part of this argument. But quite often we will correct for the number of comparisons we do in an article in an analysis. So when data are open, what happens then? Well, the top is the same as before. We get this one comparison, one statistical test, and one publication. But then the data then goes onto a server somewhere. Somebody else then does this second comparison and publishes this in another article. So now, in these two different situations we have here, the one on the left and the one on the right, what are the differences between the two? This one, that there are simultaneous comparisons going on, and here there are sequential comparisons going on. But when you kind of like boil down to the differences, the two differences that exist between the two, the first one is the timing of the test. These ones are done together. These ones are done at different times. And the second is who does the test. Firstly, this one is the same person. Here we have two different people doing the tests. So this is the difference between simultaneous and sequential analyses. And we'll get back to this later when we then talk about multiple comparison correction. So building up on this argument, I've now talked about simultaneous and sequential analyses. We're now going to spend a lot of time talking about statistical testing and sequential correction procedures. It sounds quite dry, but it actually is the funnest part of the talk. So if we just zoom back a bit and think about what is the point of statistical inference, and this is all I'm talking about when I talk about open data at the moment, is doing statistical inference on open data. There's many other uses you can use open data for. I'm just talking about statistical inference. And every time I've given this talk, somebody usually criticizes me trying to summarize statistical inference within one sentence. So I'm quite happy that you're muted. But from a collected sample, we try and infer properties of a larger population. That's kind of what we're trying to do a lot of times when we do experiments. And in practice, we're trying to find a trade-off between limiting our false positives and limiting our false negatives. And we want to maximize our true positives, obviously. So there's some trade-off going on here where we want to where we don't want to think things that are incorrect are true, and we don't want to think things that are actually correct to be false. And I'm going to talk now about the null hypothesis significance testing framework, i.e. p-values. And obviously, I'm sure many of you are aware that they're not very popular at the moment. And the reason why I'm going to talk about them is a lot of people, even if they don't like p-values, are familiar with p-values. And when we talk about multiple comparison correction, even though in other frameworks you still often have to do it, most people are familiar with the different ways people do it with p-values. So that's why I'm demonstrating this with p-values. But the problem exists regardless of framework. So I'm going to talk about p-values, but the problem that I'm going to highlight has nothing to do with p-values. Okay, going back to, that was a parenthesis there because people sometimes criticize me for using p-values. So with p-values, we often try and say something is statistically significant when p-values are under some threshold alpha. And now we're just going to make a very silly argument here, but I'm talking about this false negative, false positive ratio. If we set alpha to 1, then p less than 1 is significant, and this will entail we get all the possible false positives, but we get no false negatives. So if we only cared about false negatives, then obviously having an alpha equals 1, even though it's completely absurd, it would be the best thing to do. And conversely, if we had an alpha equals 0, then p less than 0 is significant, and this will entail we get no false positives because nothing will be considered significant, but we would also get all the false negatives. So we often try and find some kind of convention, and different disciplines have their different conventions about where alpha should lie. 0.05 has been popular for a while. People are now arguing those who have been using 0.05 should have a lower alpha. And nowadays, and in physics, for example, they have a p-value considerably lower than neuroscience. So the multiple comparison problem, most people are aware of this, but if people are not aware of it, I'll just give a very quick summary. Let's imagine we have 2 different schools and we collect data from these 2 different schools. And we first see if there's a difference between grades. We then see if there's a difference between height between students. We then check the math skills and so on. And eventually you'll find something that is significant, i.e. a false positive. The more comparisons you do, the greater the chance of getting a false positive. So here on the x-axis, you see comparison number, so the number of comparisons or statistical tests you do. And on the y-axis here, the probability of at least 1 false positive. And then this dotted line is the 0.05 trade-off that I talked about before, that we've decided is the kind of balance we want between our false negatives and our false positives. And if we do not correct for multiple comparisons, we see that we go very far away from this ideal line very quickly. So to correct for this, there are multiple procedures to correct for multiple statistical tests, such as Bonferroni correction or false discovery rate, and so on. And the idea there is to kind of bring this line back down to the alpha line over here. To illustrate what can happen if you do not correct for multiple comparisons, this is quite a famous example from Bennett et al. In 2009, is that in a dead salmon, if you do not, and you put a dead salmon in an fMRI machine, you find statistically significant brain activity if you do not do any correction for multiple comparisons. So this shows why it's really important, because obviously I think everyone agrees that we don't want to infer brain activity in dead salmon. So for those unfamiliar with multiple comparison correction and how this works, I'll just show a very quick example of Bonferroni correction. I think most people are familiar with this, but just so we have a nice similarity with the sequential correction procedures I'm going to demonstrate a little later. If we do m number of statistical tests and we set a statistical threshold of alpha, the Bonferroni correction is alpha divided by m. So if we set the alpha as 0.05 and we do 2 tests, we have a p less than 0.025 is what we have as a significant threshold. And this is a way of correcting for the multiple comparison for the multiple comparisons. Now, this is where it gets fiddly. So we have so I'm now going to talk about a concept called error rates, because these correction procedures are about restoring the trade-off of the false positive and the false negative and the false negatives, but restoring in relation to what? What are these different, when are these different comparisons grouped together? And when are they kind of like separate comparisons that you don't need to correct for? And you can think of error rates being on this, you can relate error rates to a spectrum of different extremes. On one extreme, you have the error rate of each individual statistical test you do. And in this case, you would never do multiple comparison correction because all you care about is the error rate of each statistical test. The problem with this extreme is if you hold it, you then then you get to problems like brain activity in a dead salmon. So people often, even though some people do argue for this position, most people are arguing, no, you should correct for something more. Then the other extreme is called experiment-wise correction. And this was a position argued by Ryan in 1959, which is also considered a bit too extreme because should you correct for every single variable that exists in your data set? That seems a bit too extreme as well. So there's a new concept called family, or I'm going to introduce a concept called family, or it's not a new concept, it's a very old concept. And family just means a set of related tests. So, and it's somewhere on this spectrum. Now, if you go into statistical literature or look at statistical practice about what people do, the definition where family lies on this spectrum could be absolutely anywhere. There are some people that passionately argue it's very close to the test part in the spectrum, and some people argue it should be a considerably higher, and some people will consider it being somewhere in the middle as well. It can be almost there is no consensus within the field. There are some consensus about what family entails and why there are why certain tests belong to statistical family. So there are basically two different branches. So there are several different consensus definitions, but these consensus definitions still lead to, it can almost end up anywhere on the spectrum, just so you know. But generally you find that there's two different kind of concepts or two different branches that people talk about when they talk about what constitutes a statistical family. The first is if you're just doing basic data dredging or exploratory analyses. So if you don't have any clear hypothesis, you're just testing every single possible comparison you have in your data set, then they should be considered part of the same statistical family, and you should correct for the comparisons that you're doing because you have no clear hypothesis. Second, if you're doing a confirmatory analysis and you're answering a similar or the same research question with the statistical tests, then they're part of the same statistical family as well. Problem here is we've now introduced new vague information of what is a similar research question. So these definitions are unfortunately broad, and you find that in the statistical literature, people say things like this, which I think sums the situation up quite well. So it says there are no hard and fast rules for where the family line should be drawn, and the statistician must rely on their own judgment for the problem at hand. So if you're hoping for me to produce a definition of family, that's not going to happen because very good statisticians have not resolved this problem. However, looping back now to the idea of sequential analyses, regardless of the definition of family, regardless of what the statistical family is there anything about sequential analyses that creates a new statistical family? So now going back to the first part of the talk where I said this is the simultaneous analysis situation, this is the sequential, and I said there were two differences between the two. So these are the two differences for sequential analysis compared to simultaneous, and do either of these two create a new statistical family? The answer seems to be no. And the argument that we put forward for this was a reductio ad absurdum, which is basically we accept each of these to be true in turn and show it leads to a very strange conclusion. If time makes a new statistical family, then all I need to do to correct for multiple comparisons is just wait whatever days, whatever time we say creates a new family, just wait that number of days. And so let's say we decide it's 2 weeks, then what I can do when I have a dead salmon is just wait 2 weeks for each analysis of each voxel. And then eventually I will have significant activity in the dead salmon and say I've done some multiple comparison correction by waiting. And obviously that seems a very absurd conclusion. So then time cannot make a new family. If the person matters, then another alternative we could do to correct for multiple comparisons is crowdsource. So I could then send each voxel of the dead salmon out to onto some crowdsourcing platform, get the data back, and then publish my article of brain activity in a dead salmon and saying I've multiple comparison corrected by crowdsourcing, because it's different people did the different analyses. Again, this seems absurd. So neither of these two seem to be enough to create new statistical families. So nothing about the sequentialness of analyses generates new statistical families. So then the rule of thumb we propose, it's not a perfect rule by any means, but if you would correct for tests simultaneously, then you should correct for the test sequentially as well. So does this matter now? And this is where, so for example, if you're to draw your line of, define your statistical family down here somewhere, then when you're doing simultaneous analyses, you're generally not going to correct very often when you're doing simultaneous analyses. So that means you don't have to correct when you're doing sequential analyses either. And obviously that has more impact if you have a very large definition of, if the definition of family creates very large families of statistical tests. However, now what I'm going to put forward and what we kind of stumbled upon in this paper is there are some reasons why open data pushes the size of the family to be slightly larger. And that was supposed to be an arrow. It wasn't the best of arrows I've ever drawn. So just to reiterate this definition that exists, and just to reiterate, there was two different branches, exploratory and confirmatory. And like I said, we're going to get into the definition of exploratory and confirmatory research. And that's exactly where we're going to go now. And probably the most famous or the most prominent definition at the moment to demarcate what is confirmatory and what is exploratory research is Wagemakers et al. 2012 paper, which argues that the only way we can class something as be sure it is confirmatory is if we do pre-registration before the experiment. And the reason for this is because that's the only way that the kind of like the scientific community can be sure that exploratory analysis has not been done and being masked as being confirmatory. That's the motivation behind this. But if we accept this definition, and this is what I'll get to in the next slide, open data reuse has to be exploratory. And alternatively, sorry, statistical inference has to be exploratory. I should point out now, as a side note, there's several different uses of the word exploratory that's going to occur. At the end of the talk, I'm going to talk about exploratory data analysis, which is slightly different. Anyway, but it's exploratory in the terms of creating new statistical families. So, or that they're part of the same statistical family for statistical inference. If we don't like this conclusion, we may need a better definition of confirmatory and exploratory research. That is possible, but at the moment, it seems a good definition. So this is currently where I stand, but this is a possible way out of this conundrum. So why do I say that it's often exploratory? First, all non-pre-registered studies are exploratory and that means all sequential reuse and pre-registered analyses, they're part of the same statistical family, and therefore they should be considering sequential correction procedures that I'll talk about soon. But further, and this is where it gets kind of very fiddly, is pre-registering new analyses, if influenced by the knowledge of the published data set, that also has to be post hoc and exploratory, because you can't, because if you're using information from, if you're being guided by the data set, then you can't really call this confirmatory research in the same sense as this definition, when you're supposed to pre-registration before you do the experiment and before you know what the data looks like. Here, if you're pre-registering and you already know some of the results that have been found on the data, it's possible that that's guiding your methods for the data reuse. So if we accept that, then even if you pre-register your analysis, it's still, you can't behave like you have no knowledge of the previous uses of the data set. So that also has to then be classed as post hoc and exploratory. And if then this is also classed as exploratory, then the data reuse families become quite large, because as soon as the data results are known, then the argument here seems to be, and that all reuse is then part of the same exploratory family. This is maybe a bit extreme, and there are ways you can justify this. This is not the case, but then we're starting to tweak the definition of the Varga-Marcus demarcation of confirmatory and exploratory analyses. So I've now argued that sequential correction may be needed. So how does one do sequential correction? I talked about Bonferroni correction a while back. How do we do sequential correction procedures? And in the paper, we discussed 3 different ones: alpha spending, alpha investing, and alpha debt. There are others out there as well. Alpha debt was something that we thought up of, that we made up, and the other 2 were more established in the literature. The aim is to control for tests sequentially, so you evaluate each test as you do them instead of doing them simultaneously. An important thing that you can't do is, let's say the first analysis finds a statistically significant result. By doing these sequential correction procedures, you're not supposed to be able to revise and say, well, no, that's no longer a result. We're supposed to preserve the results we have. So I'll just go through an example of alpha spending. This is kind of like quite similar to the Bonferroni correction. We set first an alpha 0 to some value, let's say 0.05. And this is kind of like the alpha value in simultaneous correction. Then on the ith sequential test, we choose an alpha I. And then this alpha I has to fulfill this condition, that the sum of all the alphas that have been used has to be less than alpha 0. So if alpha 0 is 0.05, the sum of all the tests used has to be lower than 0.05. So for example, alpha 1 could be 0.025. That's that's 50% of this. And then alpha 2 becomes 0.0125, and so on and so on. And these were just some simulations that we show in the paper to show that this figure I showed before, showing when you have more comparisons, the probability of false positives increase. Alpha spending and alpha investing ensure that we stay on this dotted line. Alpha debt, we knew when we designed it, doesn't actually keep this, but it has some other benefits as well. So, oh, this slide came out a bit wrong, but so I said this was going to be the largest part of the talk. The next 2 are going to go considerably more quick. Oh, this slide form came out quite badly. Okay, so sorry about this. So we did so now I'm going to talk about this empirical example that we did. And we used 1,200 subjects from the HCP open dataset. We used 68 measures of cortical thickness. These are going to be the independent variables. And then we did 182, we took 182 behavioral and personality measures that exist in this data set. And what we then tried to kind of like imagine was that we went 182 different labs that did 182 different analyses where they compared, for example, working memory performance in relation to these 68 measures of cortical thickness. And we then did simultaneous correction for each of these 68 independent variables. And so I'm going to walk through this graph quite slowly, but what we imagined was there were 68 times 182 different comparisons. So if we corrected for all of them simultaneously, so this is kind of like a baseline, we will get two different findings that was considered statistically significant. If instead we sequentially uncorrect, so we don't do any sequential correction, so we do 182 separate studies where we do these 68 tests, and we only correct for the tests we do within each study. This is kind of the practice we're doing at the moment. What happens is we get a considerably larger number of significant findings or significant tests. Now the sequential procedures, they come out slightly differently, where we see, I'll just talk about this one. So alpha det, that mathematically has to be as around Bonferroni or greater in the number of findings it finds. And alpha spending and alpha investing only, so we ran these 100 different times, randomizing the order of tests, and we see that the average here was around 0, just above 0. So they very rarely find these tests, and given that Bonferroni correction is known to be conservative, these two are more conservative than the Bonferroni correction, which is not so great either. If instead we look at, like, if we consider each, so there were 68 possible findings in for each study. If we look at like the number of published articles with positive findings, where, and by this I mean if there was at least one significant finding that could result with an article claiming they found a statistically significant result, what happens is if we don't correct sequentially, we have a large number, we still have around 30 different publications from this data set, where if we corrected for all of them at once, we would have 2. And the sequential corrections work around the same. So starting to sum up and get to the solutions, I talked about these different desiderata at the start of the talk, and it works out that it becomes quite hard to accept all these 3 if we use any of these correction procedures. So for example, with alpha det, I showed you before that this, in the simulations, it goes above that dotted line where the desired false positive rate was. But for example, in alpha spending and alpha investing, due to the ability to actually detect true positives decays quite quickly, there's more incentive to restrict open access to the data set. And there's also arguments for why alpha spending decreases the sharing incentive. Alpha investing also requires the order of tests as well, which is quite hard to do unless you restrict the access of the data set. So now I'm just going to very quickly talk about possible solutions in the last 5 minutes. I think I went quite quickly for this example, but to summarize, we saw a large increase in the number of published studies that have a high chance of being false positives if we don't correct for the sequential comparisons. So possible solutions. One thing we can do that is possible, I talked about this issue of confirmatory and exploratory analyses, and it could be quite hard to justify analysis being confirmatory. So one way we could do it to maintain the current definition by Wagemakers et al. Is to have a grace period. So when we publish open data, maybe we can publish the descriptor of the data and allow people to pre-register ideas of what they could do with it before the results are known and before everything converts to being exploratory. There are other ways we can go about maybe coordinating the decay of the alpha values a little better. This could be quite hard to implement, but I won't talk about this one too much because it's more of a technical solution. An alternative way, which is quite big in machine learning at the moment, is to have held out data on data repositories. And one reason why you do this is because then you can query your results against some held out data, and you're very sure that nobody else, that you haven't fit your data to that, and you can track how many times people test their results against held out data and so on. So this is a good way to make sure that people are not using, so this is a good way to be able to verify that you've not, to test the results. And it's a very, like I said, very common machine learning. There has been concerns voiced recently within the machine learning community that there's a possibility of overfitting if you still use the same held out data for a long time. And recent research that came out last year, I think, said this doesn't seem to be a problem unless the data sets are quite small. And that's when you start to see this overfitting occurring. And our data sets that we use in neuroimaging are very small in neuroimaging, in machine learning terms. Another way, like a very easy thing we can do now, is if you're publishing, if you're doing statistical inference on open data, and you're declaring it's a confirmatory study, one thing to do is just state the motivation of the statistical family. Why? What are you correcting for, and why? And that just being open about this will at least at least reveal to people why they're not correcting or why they are correcting, and that would be a good thing to do. A final thing is to try and argue that we should have the minimal family size possible. And I disagree with this perspective, but that's something that people are arguing for, that we should somehow have the smallest possible statistical families. And I'm actually writing up something against this position. Alternatively, like I only talked about statistical inference at the moment, there are some other ways we can get out of this. It's possible Bayesian statistics can help us, because how they deal with multiple comparison correction is to somehow circumnavigate this problem by things like partial pooling and weakly informed priors. So this is, I've got a question mark here because I'm not completely sure if it solves everything. There's also some really interesting stuff in machine learning about reusable holdout data. So you can actually reuse the holdout data, the test data set more and more. And the final thing is to reclassify all open data results as exploratory. And this is where I said there's a slight difference in definitions here. I don't mean we do exploratory statistical inference, but that we're doing exploratory data analysis, which is a slightly different way where we don't necessarily need to do statistical inference in the same way. And some people argue, well, this may relegate results on open data, but I disagree, and hopefully would elevate exploratory data analysis because it's an important part of the scientific process. And I've published some articles arguing for this quite recently about having open exploration. So just to wrap up, the reuse of open data entails it decays in its use value for statistical inferences, as it will detect more false positives. We can improve upon the situation today with sequential correction techniques, but it's still not optimal. We need open data, but we should be aware it's not a free lunch, and the role of data collection never stops. And in all this, replication is always going to be crucial. And open data does have other uses than just statistical inference. For example, using it as replication, using it as training data, and so forth. So that was all. This also got a bit weird there, but thank you to my my funding, the Knut and Alice Wallenberg Foundation, and the co-authors. And if you need to get in contact with me for some reason, there's some information. So that was all. Thank you.
Thank you very much, William, for this presentation. I have to confess I'm not familiar very much with what you have talked about today, so I had some difficulties here and there at grasping the main concepts. But I have a question, and when you talk about comparing different, sequentially, right, the analysis of the data, and then you calculated the false discovery rate, is that correct? I would like to understand, like, which are the variables that that enter into the game here? For example, I'm not sure I'm asking something meaningful, but I try. Like, for example, the reproducibility of the pipeline that is used to analyze the data. Is it one of the factors that is taken into account when doing these kind of experiments? Or it's just like we have a bunch of pipelines, we compare what we get and see if we actually get, or I am misunderstanding completely?
it's not really multiple pipelines in this case. It's more that, or it could be. So for example, let's imagine a neuroimaging data set, and we want to test the idea that working memory performance can be explained by brain data. And firstly, what we could perhaps start off doing is looking at individual brain regions. And that could be one way people could analyze that and publish that, and then, or maybe they found nothing. Another way is you could then use the brain data in a slightly different way, so maybe with networks or something like that, and still try to explain working memory performance. And then it's possible to argue that if the research question is using brain data to answer working memory performance, and you've got two different pipelines, they're still trying to ask the same research question. And that's why you should maybe correct for it. But multiple comparison correction is just not about different pipelines, but also different variables. So you could also imagine one group using, let's just say, all the left side of the brain, and another group using all the right side of the brain. Then you've got different comparison or different variables going into the analysis there as well. Did I answer your question there?
Yeah, I think so. But so when you say that one group uses the left part and one group uses the right part, but you mean of the same data set?
Of the same data set, yes.
Okay, so the core starting point is that the data set is always the same.
Yes, and then that leads into very interesting problems that I don't have the answers to at the moment. Is like, well, what happens if we start combining open data sets and so forth? And,
yeah, okay, and that scales up.
Yes, I don't have the answers to that yet. It's more highlighting that there is this possible problem. Maybe if we don't start pooling or selecting portions from different data sets, we can solve this problem that way as well. It's a possibility.
Okay, great. Thank you very much. So Franco Pestilli has a question.
Hi, William. Great talk. And I have a question that might be a little bit peripheral to what you presented, but I think is on topic. And so pre-registrations are often criticized for two reasons that are interrelated. One is that it locks you into a specific mindset. And we know as we do science, often things change. We learn from the data in a certain way. But also, in a certain way, once you pre-register, you had to finish a project that might not be interesting any longer, not just for the researcher, but for the community. And at the same time, the same locking mechanism forbids flexibility and creativity to emerge. And I understand this pins against what you've been saying and what many of us have been saying about the statistical version of this, but we probably need to approach this and think about intermediate alternatives that we can develop. Have you given any thought about what could be a way to approach a pre-registration from the statistical point of view, so that you don't have to give up completely the idea, you don't have to commit completely to a specific idea, while maintaining all the benefits of the pre-registration from the statistical point of view? I hope the question is clear.
Yeah, it's an interesting question. It's a really interesting problem. And I guess the way I see it is, okay, so the way I see this is I believe that we are sometimes, and I was kind of touching upon it towards the end, is we're underappreciating exploratory research. And that is where the creativity should occur. That's when we should be very creative. We should test lots of things. Science isn't just a confirmatory game. We're supposed to get our hypothesis from somewhere and that we want to confirm. And the point of pre-registrations is really to lock in the confirmatory aspect of the research. In my opinion, we don't need to have pre-registrations for the exploration parts. What we should do, however, is what we've argued is maybe be open when exploration has failed, because that also, so to be as open as possible with the exploration you've done, like put it in GitHub repositories, write a small detail about what you did and what failed, so people won't necessarily do the same exploration one more time. and give them DOIs, and so it can be citable that people tried this and failed. And when it is successful, we can publish that, publish exploration. There are certain, I think cerebral cortex has exploratory reports now. So, and that we appreciate that these are preliminary results that haven't been confirmed yet, and we still need them to be confirmed. And as long as we understand that truth, that the scientific truths we're trying to get at are not just binary significant, this is now true, this is not, but a process of exploration and confirmation, I think we can solve this issue that you're saying that people think pre-registrations are too creative, because they're only really for a portion of the scientific process. And we need to ensure that we don't forget that exploration is really important. Sorry, I hope I answered your question. I just went on a tangent talking about exploration.
I see that Jeff has a question.
Yeah, hi. I'm not really sure how to phrase this exactly, but I guess the broadest way to ask it is, where do you see the role of something like meta-analysis here? In the sense that if we have, let's say, open data, there's to some extent less incentive for people to collect new data every time they want to do an experiment. There are other data sets out there that you can sort of piggyback onto, or be a data parasite as you were describing it. So I'm wondering, in the end, let's say I wanted to look at all the studies that had examined, I don't know, hypothesis X. But if a lot of those studies are based on the same data sets, does that maybe reduce the ability of meta-analysis to tease out which effects sort of, quote unquote, were real across a large segment of the data that exist, if they're all based on the same data? Or do we not know that yet?
So I'm unfortunately not an expert in meta-analyses. And in all the different protocols that go into it. I know, for example, so I would hope, for example, in the screening and the filtering process, there is some consideration if the data source is the same, because especially if they've done the exact same test or the exact same sort of analysis, and they're both being weighted in if there's an effect in the data, it's not really a meta-analysis anymore. It's a more of a multiverse. And it's like a mixture of multiverse and meta-analysis then. And that obviously, conflating the two doesn't seem to be the best. It would be my... Did I answer the question there?
Yes, but so the second part of this was about how do we, if we're going to say that what we want to do is treat all of the data that exists as sort of opportunities for exploration, right? Then to some extent, your triangle, I feel like, kind of becomes a square, in that I would say there's also sort of, where does the pressure come from for us to collect new data if every time we wanted to explore something, it was a reasonable and viable alternative for us to just look for the extant data and use those instead?
Well, obviously, so when I was saying that exploration is an important part of the scientific process, it's not the only part. There's an equally important part is the confirmation process. And what this is kind of trying to get at is that doing the confirmatory steps on open data could be quite hard, although at least it's not unproblematic. There could be some issues, and this is what the talk was trying to highlight. And so the reason why data collection, I said at the end, data collection never stops, is because if this use value of data sets to find statistically significant results on data decreases because we've used it so much, we need new data all the time. Otherwise we're just going to be able to prove, we're not going to be able to prove anything is statistically significant because the alphas are going to be so small.
Right.
So yeah, more data always needed.
Fair enough. Thanks.
I have another question which might sound, again, a little bit trivial, but I'm very curious about all this new world that you are just opening to me. So, so you're talking about exploratory and confirmational research and then data set. Are there like philosophical reasonings more than practical about when a data set that was collected for exploratory can be used for confirmation or the other way around? Or another way to put the question is there a way to optimize the amount of data that we collect in order to make sure minimize or optimize, I don't know which word to use actually, in order to make sure that we don't waste our resources and we use our data at their best potential?
That's an excellent question. And I wish I had a really excellent answer to that. I mean, that
an intuition would be enough.
I think it's almost a cop-out answer, but it's going to be like, it really depends on the situation. So, for example, again, with let's say with neuroimaging, with fMRI, we've got a lot of resting state open data now. We don't maybe need more resting state open data for exploration purposes. If you've got a confirmatory idea, maybe we need more, but we probably don't need, we probably don't need more of that type. But more data in more situations would be good. So to make sure we have diverse number of data available, and that may mean it's a really hard question, and that's the only thing, is that it really depends. And I think the best way to go about, so one of the ways I was trying to go about saying how you can maximize the use for confirmatory research is, for example, that pre-registration grace period. So if we start making like announcements like this data set is going to be released soon, and then people can start doing pre-registrations in order to be able to do their confirmatory research on that data set. So then we maximize its use for confirmatory research.
Yeah.
But I think a data set always has exploratory value regardless of how often it's being used. And this
I'm not sure, because they get old. Like the techniques get old, and so, you know, so data sets get old. And this is something that is not always actually considered in these kind of discussions. But if I look at CT images of the knee, I work in MSK of 20 years ago, we can trash them, you know, so there is also this aspect. But I don't want to take too much time on this. That is a bit, going a bit long tangent. Guiomar has another question.
Hi, thank you very much for the very nice talk. I just, it's a curiosity, and I said how this relates to the NARPS study. I didn't follow because I don't know if Rotem is here and can answer, or you can answer. Yeah.
I would say they're slightly different ideas, because one of them is more of a because they're approaching hypothesis in a slightly different way. So the hypothesis in the NARPS article, as far as I would say, is like, is it the case that they all get the same result? Whereas, so it's not as, it would almost be an absurd thing to do to get all the different groups in the NARPS project to correct for the other people, because their analyses are independent of the other ones, because it was more of a competition or to see the differences. So in those cases, it doesn't make much sense. But I feel there are, if it was the case that they were doing that, that these 70 groups were independently looking at the NARPS data set to try and prove the hypothesis with different techniques or whatnot, then maybe they should start considering correcting for multiple comparisons. So if they were published separately and completely ignoring each other, then maybe it would be a case to start thinking about sequential correction procedures.
Okay.
That answers the question. Sorry, I always need to make...
I was thinking, oh, because they are testing the same hypothesis, maybe they could apply, but it's true that it's more exploratory, and it's like they're...
So it's always quite tricky, because usually when you're doing like simultaneous hypothesis testing, because they're all trying to answer the exact same hypothesis, where usually when you're doing corrections, you're doing different tests to answer a similar question, where here they're doing the same data to trying to answer the same hypothesis. So it's a slightly different issue, I would say. And it's really hard to specify what. I am sorry if I'm answering it.
Yeah, okay, thank you. Yeah, thank you.
Okay, Paolo Belardinelli has another question.
I guess you're familiar with the cluster statistics conceived by Eric Maris. that produces a p-value, and it's quite popular in MEG, EG. My question would be, if I'm applying the cluster statistics to different time chunks of the same signal, I need a correction, right? So I end up with several p-values and several different cluster plots for the different time chunks, but it's the same signal, and I'm analyzing it longitudinally. Sorry?
So it really kind of boils down to like what I was saying, the idea of what a statistical family is, and they're going to definitely be possible to argue both ways. That
Okay.
You can probably meet a statistician who would argue that they are the same family or they're not the same family. It really depends on the hypothesis you're asking. Okay. And I apologize that I'm being very vague. It's just in this article, we're trying to be extremely neutral about what a statistical family is. So I understand that people want to know, like, is this a statistical family? Is this a statistical family? But it comes down to, what are you trying to say with the data, with this when you're doing statistical inference? And I think it's always a good idea to reflect on if they're fulfilling these criteria, for example, that they're answering the same research question. And I know with cluster statistics, if it's consecutive time points, you can also add in cluster statistics through time and frequency as well. I believe, from what I know of the cluster statistics, and that exists in the software like Fieldtrip and things like that. But if they're kind of like separate, disjointed time points that you're considering, it really depends on the inferences you're trying to make. And this is where statistics is hard. It requires us to think more. It's not just like a magical button that we press and it gives us an answer. It requires this kind of like this more layer of philosophical thinking about our hypotheses, about our the comparisons we've done.
Thank you very much.
There is another question. Jeff, do you have another question? Go.
Hi.
Quickly.
I was just thinking during that last question, I don't mean to pin you down about what is or isn't a family of statistical tests, but I was wondering if maybe, in the sense that when you're calculating a p-value, it's sort of it's a conditional probability, right? And I'm wondering if maybe you could conceptualize the family of statistical tests based on the independence of two hypotheses. In other words, that the outcome of one test is, in some sense, not conditioned on the outcome of any other test or of some other test to determine whether it belongs to a family.
So still, again, unfortunately, no. So people, even if there is some dependency between tests, and I'll answer this very quickly, but you do see people argue them being the same statistical family. So independence is not the necessary condition for it being two different statistical tests. And unfortunately, it's just you see the answers going everywhere. I mean, I'm just like you. I was looking for a definition. I spent an entire summer looking for a definition and got, I just went deeper and deeper and further back into the statistical history of families. Okay. And I didn't get anywhere.
Well, I tried. Thank you. It's good to know that at least somebody went and looked and that turns out not to be the case. Thank you.
William, thanks again for being part of this workshop. And again, great to talk. And I'm sure that for your peers, they understood a lot. For me, you really opened a lot of a new world with a lot of new questions. So thank you very much for your contribution.
Thank you for having me. And yeah, anyone just let me know if anything was unclear later. I can try and clear it up in emails or whatever. Thank you very much.
Great. Thank you. Bye-bye.